Okay, good morning, everyone. Welcome to the GIST Sea Level Rise seminar. We're very glad to have Aurora Basinski-Ferris, who is a final year PhD candidate at the Center for Atmosphere Ocean Science at NYU's Courant Institute. And they are working on problems related to large-scale climate and ocean dynamics using various methodologies, including response theory to understand perturbations of the climate system, developing theory from simplified geophysical fluid dynamics models, and working with the MITgcm ocean model run in idealized setups. Aurora received an honors Bachelor of Integrated Science with a concentration in mathematics from McMaster University and is the winner of the Sandra Bleistein Prize, awarded for notable achievement in applied mathematics or computer science. The title of their talk today is Dependence of Regional Sea Level on the Depth of Meltwater Input. Welcome.
Thanks for the introduction, Patrick, and thanks for the invite to talk to you all today. Let me share my screen. Oops. Where is my presentation? There. Hopefully you all see that. Cool. Yeah, so I'm going to be talking about the dependence of regional sea level on the depth of meltwater input. And this is work that was done with my PhD advisor, Lorzana, as well as with Emma Beer and Ian Eisenman. And throughout the talk, just feel free to interrupt me if you have questions so that we're all on the same page. So I'm going to start off with some background that I think is probably pretty familiar for this group. Antarctica has been experiencing mass loss in the observations. So this can be seen, for example, on the bottom left plot here, where we're looking at mass change from 2002 up to present day, and we see this very clear downwards trend. If we start to look at the spatial distribution of where this is, we could, for example, look at the top left plot, which is looking at elevation change on the ice sheet from 1978 to 2017. And what we find is that there's what we find is that there's primarily loss in the West Antarctic ice shelves. So you can see those kind of green regions over here is where we're experiencing loss. There's quite a bit of uncertainty in the future about what's going to happen, which I'm not going to touch upon. But regardless, there's significant changes that are projected. And for that reason, we need accurate ways to be able to make sea level projections in response to this meltwater. And in particular, we want to be able to make them accurately on the regional scale. So the majority of the mass loss that's occurring is from what's known as basal melt. There's a little schematic of basal melt on the top left here. So the idea is that the ocean water is interacting with the ice shelf that's overhanging the ocean. And then the meltwater exits the ocean or the ice shelf cavity. And what's been shown both in observations and in some modeling studies is that this meltwater tends to mix and settles at depth in the water column. So modeling studies have indicated that there's kind of various turbulent mixing processes that result in this occurring. But we can see it in the observational evidence if we look at the bottom left plot here. So this is data taken near the Dotson ice shelf, which is one of those West Antarctic ice shelves. And the x-axis here is the distance from the Dotson ice shelf, and the y-axis is depth. And the redder colors are indicating higher concentrations of meltwater. So what we see is that the highest concentration of meltwater near here is at around 500 or 600 meters. So we can start to think about how this is dealt with in models. So there's been a lot of effort to couple ice sheet models fully with atmosphere ocean GCMs, but at least for the current generation of CMIP 6, for example, atmosphere ocean GCMs are generally not coupled to ice sheet models. And so the typical approach that's taken is what's called a hosing experiment. So the user basically makes a manual decision about what spatial distribution the meltwater will be put in at, including in the vertical, and then also has to specify the temporal evolution. And the typical choice that's done is that meltwater is put into the ocean at the surface. And so what we've been trying to get at is getting a first order understanding of what's happening here, because we know in observations, meltwater tends to come in at depth. But the typical choice is to put meltwater in at the surface in models. And so the central question that I'm going to get at in this talk is, what is the dependence of dynamic sea level on the depth of meltwater forcing? And I'm going to take two different approaches, and both will be talked about today. So the first is looking at some results in MITgcm set up in idealized geometry. So here we're going to be looking at a single basin setup that I'll expand on a little bit more in a second. And then after that, we're going to turn to a more simplified model called a 2.5 layer model. And we're going to try to develop some numerical and analytical results there that we can kind of port back over to MITgcm to try to explain results that we had in that setup. So yeah, as I was saying, the MITgcm setup that we're looking at is in a single basin. So the bathymetry can be seen in panel A here. So basically all around the basin, there's these linear continental shelves that decrease linearly down towards the bottom of the ocean, except for in this one region, which is representing like an idealized Antarctic circumpolar current region where we just have a sill. And that's also where wind is applied. There isn't wind applied anywhere else in the basin. And to start, the first thing that we do is just make like a very long spin up run to try to get the ocean into equilibrium with prescribed boundary conditions. So for this, the boundary conditions that we're using are in panel C and D. So they're relaxation profiles of both sea surface temperature and sea surface salinity. So the idea is on a particular timescale, you're just nudging back the salinity or temperature to this profile. And we run this forward for about 6,000 years until things come into equilibrium. But then we can start to think about how we actually want the model set up when we're going to start putting in meltwater. And the approach that we're taking here is following some previous studies to try to basically isolate the ocean response from our surface boundary condition. So the idea is that if we had continued using a restoring boundary condition, when we put meltwater in different places, we might change, for example, the surface temperature differently. And so our restoring boundary condition would then do something different at the surface. So instead, what we do is we take a look at the fluxes from our spin-up run. So here on the left, I have the global mean heat flux into the ocean in the spin-up run. And on the right, I have the global mean salt flux into the ocean in the spin-up run. And we basically extract time periods where this is near zero. You can see that it's kind of equilibrating out to zero on a long time scale. And then we just take fluxes out of there and we impose them constantly onto the ocean. So as an example of what this looks like, here's like one of the ensemble members that we would make. So this is the mean over a 25-year period. And so there's latitudinal and longitudinal structure, but this would be constant in time. And this is all of the ocean would ever see in our runs. So what we do for each ensemble member then is we like branch 3 experiments. So the first is just a control experiment. So we just run the ocean forward with these fluxes, and there's kind of no additional business happening there. And then we have 2 meltwater experiments. The first is a surface input experiment. So all along the southern boundary, at every longitude, we input volume in the top grid cell. And then the second is a deep input experiment. So at exactly the same like latitude and longitude all along that southern boundary, we input mass at 1,000 meters depth. And then we run all of those forward and we see how the sea level adjusts differently. So the key result from MITgcm is shown here on the left. So we're looking here at a 100-year timescale that's shown along the x-axis, and we have height in centimeters on the y-axis. And what's plotted is the dynamic sea level. So this sea level quantity has a global mean of 0. And it's the Northern Hemisphere dynamic sea level. So it's basically the Northern Hemisphere mean sea level minus the global mean sea level, which is why things are negative here, because you have slightly higher sea level in the Southern Hemisphere than the Northern Hemisphere. But we can look at and compare these blue and orange lines to try to get a sense of what's going on. So the light lines underneath are individual ensemble members. You can just focus on the solid line. But the blue is showing the surface perturbation experiment, and the orange is showing the deep perturbation experiment. And what we find is that we have faster and stronger adjustment in the Northern Hemisphere, which is the opposite end of the basin, when we put in meltwater at the surface compared to when we put it in at depth. So that can be seen from this blue line being above the orange line. There's a couple of different ways that we could try to break down what's happening here. But what I'm going to focus on is trying to decompose this signal into contributions from different transport processes. And in particular, I'm going to try to decompose this exact plot that you see on the left into contributions from the baroclinic processes and the barotropic processes, following a new paper, McWilliams et al. 2024. So to go on a little bit of a tangent, I'll give the basic idea about how you can do this decomposition before I show you the result. So the idea is you want to break sea level into contributions from barotropic and baroclinic transport. Here we're going to define barotropic transport as the vertically meaned transport. So it's defined with this integral here. And then the total transport is the barotropic plus the baroclinic component. And so the baroclinic component is just any deviations you have. Okay, so if we define velocity that way, we can also try to define pressure gradients that way. So we know the form of the momentum equations is that we have an acceleration term that's driven by a pressure gradient plus a bunch of other stuff that's all captured in the dot, dot, dot here. So if we are partitioning velocity in a particular way, that also implies we should be able to partition pressure in a particular way. And so I can write two forms of the momentum equation where we have a barotropic velocity driven by a barotropic pressure and a baroclinic velocity driven by a baroclinic pressure. Note that the baroclinic pressure has dependence on depth and the barotropic doesn't, because it's vertically meaned. Okay, and then the last step in this kind of broad overview of how you do this decomposition is just noting that the pressure at the sea surface is related to the dynamic sea level. So the pressure at the sea surface is equal to or proportional to gravity times the gradient of the sea level. And so that implies that you can kind of similarly decompose the sea level into barotropic and baroclinic components. I won't show how you get like a closed form for this, but from these equations, you can get a closed form for both the barotropic and the baroclinic components with kind of an additional assumption. Okay, so here's that decomposition applied to the results that I already showed. So the dashed line now is showing the baroclinic contribution to this total signal. And what we see from the match between the dashed line and the solid line is that this like phenomenon that we noticed where we have faster adjustment of a surface perturbation compared to a deep perturbation is largely coming from the baroclinic component of transport. Cool. So far what I've shown is that we have faster adjustment around the basin when we input meltwater at the surface rather than when we input it at depth. And this is mostly because of the baroclinic response. And so what I'm going to spend some more time next on is trying to develop a simplified model that can give us some intuition for adjustment mechanisms that are at play here. And so before I go specifically into the model, I'm just going to comment on like why we might want to use an idealized model. So we've noticed this phenomenon in MITgcm, and it's complex for a lot of reasons. So I've listed some things. We're solving the full Basinski equations, which are solved in vertical coordinates. There's 40 vertical depth levels that we're solving this on. This is in an eddy permitting resolution, which I may not have mentioned, but it's run in a quarter degree. So it's permitting eddies. There's a full equation of state that's dependent on both salinity and temperature. And we have a lot of background transport that we've spun up prior to the meltwater introduction. So we have transport from like both a surface and a deep cell of overturning. So when we think about like what our ideal world would be for a simplified model to try to get at what's happening here, we basically want the simplest system that can capture the relevant features that we're talking about. So the simplest system that can capture that we have faster adjustment of a surface perturbation compared to a deep perturbation. And so we know we need at least two moving layers of fluid because we need to be able to capture in some way a depth dependence, but maybe we don't need the full Basinski equations. We might be able to work with some simplified dynamics, so we might not need eddies necessarily. I'm going to show some results where we're beginning from the ocean at rest, so we're only looking at how the meltwater itself is driving transport. And we might not need a full equation of state. We could just use density without salinity and temperature. All this isn't to say that the other dynamics that are captured in a more complex model aren't important, but just what what we could boil this down to try to get some intuition about what's happening. So the model that we're going to use is known as a 2.5 layer model. There's a schematic of that shown on the right here. So this is in depth longitude space. And the 2.5 layer model is 2 active layers of fluid with densities ρ1 and ρ2 that are sitting on top of a deep abyss that's representing the deep ocean. So it has density ρ3 and it's motionless. This may be familiar to some of you. This is like within a class of models called a reduced gravity model. Usually you see them in a 1.5 layer form, but they exist for any of the n.5 layer forms. And generally they've been used to understand upper ocean processes. So they've been used for simplified models of like El Nino or trying to understand things about thermal hairline adjustment, for example. So the way that we're kind of thinking about this is that we have these 2 active layers that are the upper ocean on top of the deep ocean that isn't doing much. There's another reason that we might think that it's useful to use this simplified model. We already noted from MITgcm that this is the phenomenon that we're interested in is primarily coming from baroclinic processes. And that's exactly what a reduced gravity model or a 2.5 layer model represents. Because you have this very deep, motionless lower ocean, you aren't really representing barotropic transport because the vertical mean would be near 0. So this is designed to represent baroclinic modes, which is what we already know is important. Okay, so I'll show the equations that are defining this model. So the first are the continuity equations. So basically all we're saying is that we are conserving volume in each of these layers, and it can be advected around. And I have these 2 source terms that I've written down that are going to be pretty important when we start trying to use this for our problem, because this is how we would add additional volume into one of these 2 layers and watch how the adjustment happens. And then there's momentum equations. Yeah, don't worry too much about them, but the 2 things that I want to point out here is that they're linearized, so we've really simplified a lot of the dynamics down here. And also that everything is basically driven by gradients that are proportional to the density differences between the layers. So we're using only the reduced gravities G prime. So what matters is the difference between ρ3 and ρ2 and the difference between ρ2 and ρ1. And then when we try to map this back onto what's happening in MITgcm, we can think that maybe perturbing the upper or lower active layer is analogous to varying the depth of the meltwater input. So I'm going to show the setup here of how we're solving this numerically. So again, this is kind of a single basin domain, although things are like much more simplified now. We have latitude on the y-axis and longitude on the x-axis. We have to use some sponge layers at either end for numerical reasons, which aren't really important for the problem, but they're indicated here. They're necessary to keep the simulation stable and damp out gravity waves. But really what's important is that we have this meltwater input region, which is where we're going to activate those source terms in the continuity equations. So kind of all along this region, that's where we will put in additional mass. And then we have the rest of this purple region, where we're going to see how the rest of the basin adjusts to the mass that's put in the green region and see how that sea level and layer thicknesses are propagating throughout the basin. We have to make a couple of parameter choices. So here I'm just choosing that the density difference between all of the layers is the same and it's equal to 2. And I choose initial layer thicknesses of 250 meters. So the upper ocean that's being represented by the active layer here is 500 meters. And then we have the deep ocean below it. Okay. And then for those who are interested in the numerical approach, I'll just kind of quickly list what I did, but it's, yeah, not an important part of the talk. But as I already mentioned, we have to have sponge layers. We're using no slip and no normal flow boundary conditions along the edges of the basin. In space, we're solving with finite differences on an Arakawa sea grid, and in time, we're using a Runge-Kutta 4 solver. And then the kind of one more note is these equations, we would have to add some viscosity to the momentum equations to keep things stable. Okay. So here's an analogous plot that's showing the results from this simplified 2.5 layer model. So what I'm plotting here is specifically the baroclinic sea level. This is, again, because we know that this is dominant in explaining what happens in MITgcm, and also because the 2.5 layer model is designed to represent baroclinic modes. So along the x-axis, we have time. We're looking at a 75-year timescale. And along the y-axis, again, we're looking at height in centimeters. And this is the Northern Hemisphere mean baroclinic sea level. So kind of exactly analogous to what we looked at before. And what we find is that we qualitatively recover the MITgcm result. So we have the blue line, which is the top layer perturbation and is analogous to that surface perturbation. And we again find faster adjustment and with higher magnitudes when we look in the Northern Hemisphere compared to the orange line, which is the bottom layer perturbation experiment. So this is kind of hinting to us that some of the dynamics that were important in MITgcm and getting that result, we might also be capturing in this simplified model. If you're really staring at the slides, you might see that I have this equation down here for the baroclinic sea level. So this is the quantity that's plotted above. And it's linear combinations of the two layer thicknesses, H1, the layer thickness of the top layer, and H2, the layer thickness of the bottom layer. And there is a larger coefficient on H1. But what I want to stress is that this behavior that we see is not because of that coefficient. It's because the top layer actually adjusts out faster than the bottom layer. And that's what I'm going to show with some more plots going forward. So here's kind of a first look at what the actual domain looks like as it's adjusting. So here we're showing the thickness of each layer in this simplified model at the end of 75 years. The left column is a top layer perturbation experiment, and the right column is a bottom layer perturbation experiment. And then the top row is the top layer thickness, and the bottom row is the bottom layer thickness. So if you're thinking about this as like a matrix, like the main diagonal here, these are the layers that were actually perturbed in their respective experiments, and then the other two are the layers that were not perturbed. Okay, so first look, things look pretty similar between the left and right column between the two experiments. But what I'll highlight is the difference in the color bar here. So we're looking only at the domain north of where we input. I've also cut off the western boundary current. And what we see is that the thicknesses here are saturating at a higher level, about 0.2 meters higher in a top layer perturbation experiment than in a bottom layer perturbation experiment, which is giving us some indication that we're having faster adjustment in a top layer perturbation experiment because the actual thicknesses of the layer are adjusting faster. Okay. So to try to get into what this is, I'm going to posit what I think to be the central mechanism, and then we'll go through and show that that central mechanism is true. So the idea is that the adjustment of this basin happens in 3 steps. So on the right, this is like a little schematic of what's happening, and we have the input region. And the first thing that happens is that we have transport out of the input region in a western boundary current. So that's what this TS vector is indicating. And then we have Kelvin waves go across at the equator and along the eastern boundary. And I'll show a video in a second to show this. But basically at the end of step 2, the eastern boundary doesn't really have latitudinal dependence, but it has increased sea level compared to the rest of the basin. And then the third step, and what's really like the slow adjustment step, is that we have Rossby waves emanating off the eastern boundary and adjusting out the rest of the basin layer thicknesses. So these 3 steps are consistent with other studies that we've seen for other kinds of perturbations. So for example, in 1.5 layer studies, we've seen that these kind of adjustment mechanisms are what's highlighted. And there's also some previous GCM studies that have shown that this is the baroclinic response because of meltwater put in near Greenland. Okay, so just to show you a video of what's happening, the video that I'm about to play is the evolution of layer thicknesses in a top layer perturbation experiment. So the left plot will be layer 1 and the right plot will be layer 2. I would suggest just focusing on the left plot so that you can see what's happening. But I'll play it twice so that we can see those mechanisms. So what I saw kind of happen first was this western boundary current appeared, and then we had a wave go across the equator. We can see at this point that the eastern boundary doesn't really appear to have latitudinal dependence. So that's the Kelvin wave response that we thought happened. And now it's running forward and we're seeing kind of slower adjustment. This video only goes up to 1.5 years. So you're not going to see adjustment throughout the whole basin because the Rossby wave response is slower than that, but you start to see some of the adjustment happen. So I'll play it again just so that we can see. So we see the Western boundary current appear and then the Kelvin waves appear. Okay, so we have, we have this mechanism that we think is reasonable from previous studies. We also can kind of see it if we look at videos of how the basin's adjusting. And the question is, how does this help us with explaining what's occurring in terms of the vertical dependence of adjustment of these processes? So now this schematic, I'm looking in depth and longitude space instead of latitude longitude space. And so I can see these Rossby waves coming off the eastern boundary. And what we're hypothesizing is that this faster adjustment of the top layer thickness is because of faster baroclinic Rossby waves in this top layer than in this bottom layer. So if that mechanism holds true, then if we have faster Rossby wave fluxes in this top layer, then we're just basically going to get faster adjustment of the sea level. So I'm going to show a little bit of analytic theory to kind of prove to you that that's true. And then we'll try to take this back and show that we can explain our results using this idea. So just a quick note for the theory section, it probably won't be immediately clear how equations follow from each other, but I'm just trying to give kind of broad steps of what we did. So the very first step here is just to assume the dynamics that we think are true. So we're going to assume geostrophic balance holds in this model, and we're going to substitute that into the linearized continuity equations. And you get kind of a messy equation that looks like this, where now it's a partial differential equation for the heights, and it's only in terms of other heights. And we see this Kronecker delta here is indicating that this term is only active in the top layer. We can exactly rewrite what we had there as a system of equations. So now we're looking at the evolution of an H vector made up of H1 and H2. And we have this A matrix that's involved in this kind of evolution equation that's written below. And this is kind of defining how the heights are evolving in time. Okay, again, kind of skipping some steps, but the idea here is that we decouple these equations by diagonalizing the matrix, and we end up with much nicer equations that are just scalar advection equations in a new variable W, where W is linear combinations now of H. So we have some evolution of the W equations according to this diagonal matrix. We can solve it with some work, and then we can transform it back to the original coordinates. And we end up with these two really, really messy equations that are showing how we would expect the height in each layer to adjust. And I'm going to try to walk through what's happening in each of these layers, or in each of these equations. So based off our physical mechanism, the way that we're interpreting this is these are basically lag equations off the eastern boundary. So I have some eastern boundary time series, and at any location elsewhere in the domain, I'm related to like a time history of the eastern boundary because that was what was sending the Rossby waves. So the first thing to notice is that there's two timescales involved in these equations. There's a slightly faster timescale lambda 1 and a slightly slower timescale lambda 2. And I'm going to highlight the terms one by one. So let's look first at the faster timescale lambda 1. We see that these are active in both layers. So what I'm highlighting here is how each layer affects itself. So this is how the eastern boundary of H1 affects H1 and how the eastern boundary of H2 affects H2. So we have the fast timescale involved in both equations, but we see different coefficients on these two terms. So here, alpha 1 and alpha 2 are both positive numbers. So alpha 1 plus alpha 2 is larger than alpha 2. And we're more highly weighting this term in the H1 equation than in the H2 equation. We can kind of similarly highlight the other terms that have the fast timescale involved. So this is now how the bottom layer affects the top layer, or the top layer affects the bottom layer. But we see that this doesn't really seem to be part of our story. The alpha 1s here match. And so this is not telling us a difference between these two equations. We can then do exactly the same thing with the slow timescale lambda 2. So I'm highlighting things in pink for the slow timescale. And again, the solid lines are how you affect your own layer. So H1 affects H1. And now what we see is that we have this larger coefficient on the slow timescale in the bottom layer equation. So the kind of summary or the takeaway here is that what we've seen is that we have a larger impact of the fast timescale in the top layer equation, and we have a larger impact of the slow timescale in the bottom layer equation. And the way that this can be thought of is through me kind of telling you what these timescales actually are, which is that they're actually exactly equal to the long baroclinic Rossby wave speed for the two baroclinic modes that this model hosts. So we have two baroclinic modes and two Rossby wave speeds associated with them. And what we're seeing is a larger projection of the faster of those on the top layer and a larger projection of the slightly slower of those on the bottom layer. And we think that this is really what's determining the difference in the speed of adjustment that we see of these two layers. Okay, I'm going to show you that analytic theory was reasonable to do. So there's kind of more work that would have to be done behind the scenes to fully like make a map from the analytic prediction. But the basic idea underlying all of it is what I just showed you, that we have this faster speed in the top layer than the bottom layer. And so what I'm now showing is just a top layer perturbation experiment, and this is at the end of 75 years again. But now the left column is the prediction from analytic theory. The middle column is the numerical model. And the right column is the difference between the prediction and the numerical model. So what we can see is that the prediction is essentially explaining the numerical model exactly here. And so this mechanism that we identified analytically is important in the numerical model. And probably what's determining what's happening in the numerical model as well is this difference in the baroclinic Rossby wave speeds. Okay, I'm going to bring it back to some time series here. So this again is the same plot that I was showing you. It's the Northern Hemisphere mean baroclinic sea level and the 2.5 layer model. And the dotted line now we've added on the analytic solution. So we see that like we can explain the time series through this analytic solution. And so it's kind of largely explaining what we see in the numerical 2.5 layer model. Something that I want to stress is that this should really be thought of as like a qualitative explanation for what's happening in a more complex model, because there's lots of sensitivities that I haven't shown you here. So one sensitivity, for example, is if we start to think about what we actually, how we actually should have chosen those rows or the densities of the layers. We might want to set up the stratification not as being equal between every layer. So if we change the stratification such that the difference in densities between the active layers is larger than between the abyss and the upper ocean, we get an increased gap between the blue and orange line at a 75-year period. So if I look like right at the end of this, we're going to have more spread between those two. The other thing is that the really nice thing about the simplified model is that we've gotten rid of a lot of the dynamics from MITgcm to try to boil it down to something. But those dynamics might also have been important, and we've gotten rid of them, right, in the simplified model. So in particular, one thing that I can think of that would probably be pretty important is the background transport that already existed. The meltwater isn't just advecting itself in the real ocean or in a more complex model. So to try to get at that like a little bit, like a very rough picture of how that might change, we also have looked at this simplified model with wind applied in the Southern Ocean. So we're driving some Ekman transport. And we find again that we get an increased gap between the top and bottom layers at a 75-year timescale. So all these other things are probably also impacting the story. But we think that the mechanism that we've identified here is at play in a more complex model or in the real ocean. So a summary of what I wanted to get across here. Antarctic meltwater is often input at the ocean surface in models, but in observations, it enters the ocean at depth. I've introduced a hierarchy of models. So the most complex model, the result is in the top right here. This was in MITgcm in a single basin. And what we identified is that surface meltwater perturbations adjust more quickly than deep meltwater perturbations. We then introduced a more simplified model, a 2.5 layer model that was able to capture a lot of the key behavior of MITgcm. And then we came up with like an analytic solution for that model that really highlighted that what was happening here was the differences in the speed of baroclinic Rossby waves. So everything that I presented here is still like quite a bit more idealized than like a full coupled climate model. So I think this like motivates studies in more complex models to try to understand with realistic geometry and with coupled dynamics with the atmosphere, how the sea level is sensitive to vertical meltwater distribution. And I'm just gonna show two in progress slides before I open this up for questions to show like what we're thinking about now to add on to this story a little bit. And yeah, what we've been thinking about is trying to like bring this back to model land or like more complex model land and understand what the quantitative dependencies might be if you were actually trying to implement this in a model. And the reason for that is kind of motivated by the plots that are shown on the bottom here. So on the right, this is the plot that I've shown you many times throughout this talk. So this is run in a quarter degree, a quarter degree resolution with no Chapman-Williams parameterization on. And then on the right, what we did is we took exactly the same setup. So we have the same parameters, the same vertical diffusivity, et cetera. But we ran the model in a 1 degree setup. And now we've turned GM on and we're using a thickness diffusivity of 1,000. And so the qualitative story stays the same here. We have faster adjustment of the blue line, which is the surface perturbation, but the quantitative story looks different, right? At 100 years, the difference between the surface perturbation and the deep perturbation is much smaller in this 1 degree setup than in this quarter degree setup. And it's not immediately clear why that is, but there is about a 2.5 times difference between these two. So we've been doing a little bit of like a parameter sweep of how we might set up the model before we even put in the meltwater. So we've kind of messed around with a bunch of different 1 degree models, and we've tried 10 different GM parameters, so ranging between 0 and 2000, and 5 different vertical diffusivity profiles. And then for each of those, we do exactly what I talked about at the beginning of the talk. We equilibrate it, we like isolate the fluxes from the surface, we put those on, and then we run forward with perturbation experiments. And the results are shown on the right here. So the x-axis is the Northern Hemisphere mean dynamic sea level, the mean of the last 20 years. And then the y-axis is the count for all these different model setups that we have. And so we find that we have two kind of distinct distributions. So it still matters whether you're putting in meltwater at the surface or at depth. But the spread, like once you're like, I'm pretty sure that this should come in at 1,000 meters, the spread between different model setups is actually quite large. And so there's lots of sensitivities about how the ocean was set up that's important for this story also. The one thing that I'll note here is that this apparent overlap between the two distributions is for different model setups. So for any given model setup, you always have that the surface adjusts faster than the deep. This is overlap for like model setup A compared to model setup B is why you have some agreement there. And yeah, at that, I'm going to leave it at that, and I'm happy to answer questions.
Thanks a lot. Any questions? So I had a question about the time scale of the processes. Like if you ran out the model over a longer period, would they eventually converge together? The two different simulations.
That's a great question. So with some of the model setups that I've talked about here, I've run them out to 500 years, and they don't converge. So those lines might flatten, which means that like you're no longer like kind of contributing to the difference between the surface and the deep, but you still maintain that there's a difference between the surface and the deep perturbation. Yeah, and the timescale sensitivity is definitely kind of sensitive to how you've set it up, like how quickly those lines flatten out, but you maintain the gap. Thanks.
Really nice talk. Thank you. I especially like these last slides because that's exactly what I was going to ask, was this like quarter degree versus 1 degree. So that was very cool to see. And I guess just curious if you are interested in potentially moving to kind of more typical GCM simulations, maybe be interested in looking at those in the future, or you prefer to kind of stay in these more controlled setups?
Yeah, I think that's definitely the next step. Like I feel like this was giving kind of the most basic picture of what you might expect, but there's lots that you're missing here because we don't live in a rectangle. So I think that's the next move, like looking at how this works in like more realistic geometries and also maybe coupled. I'd have to think a little bit more about whether you should keep trying to like isolate the ocean from the atmosphere or whether you're actually interested in like you're changing the AMOC in lots of ways and you're going to have like coupled responses with the atmosphere. So yeah, I think that's like what needs to be done next. Thanks.
Cool, thank you.
Yeah, Kevin has a question.
Hi, that was a great talk, and you made a lot more progress analytically than I would have even thought possible. So well done on that. But to kind of like pull this back, like how much water were we talking when you're putting in this water?
Yeah, that's a good point. So the perturbation here is 0.1 sphere drops put in as a step function. So there's no temporal variability there.
So it's just put on 0.1 sphere drops and then it just stays at 0.1 sphere drops.
Yeah, it's a step function. Yeah,
okay,
exactly.
So compared to the total flux from the from the ice sheets, how much is that? I should probably be able to do sphere drop to gigatons in my head, but I can't.
I can't either, but 0.1 is basically like the high end estimate. That's from like the DeConto and Pollard paper. So it's quite a strong perturbation here. And
but hold on, but you have no meltwater initially, and then you have a whole bunch of meltwater, right?
Yeah,
so
exactly.
So in the real world, there's a whole bunch of meltwater, and then there's a change in the meltwater, right? So, but a whole bunch of meltwater that just comes from the climatological balance between snowfall on Antarctica and calving of the icebergs and things. That's a much bigger number, right?
Yeah, that's a good point. So yeah, there's no like temporal evolution here. We've just kind of taken a pretty large number and put it in as a step function as a first go, which I think is what you're getting at.
Yeah, no, it's just that, I mean, Letty, what's the sphere drop output of the climatological flux?
I don't know. I was just Googling sphere drop to gigatons. Yeah, I don't know. Don't put me on the spot.
Somebody, so like I think it's in one of the papers. Oh, you know what? It's in the 23 paper, and there's two bars which have one's in sphere drops and one is in gigatons. For the anomalies. Hold on, let's see if I can find it. Oh yeah, I mean, it doesn't really matter. I can't find it. The point is that that there is both an anomalous flux, right? Because the ice sheets are melting, but there's also a climatological flux, which is much larger because there's a hydrological cycle that involves the ice sheets. Now, if in any particular GCM, which I don't think would include ours, but in others, they do just put that in at the surface, right around the edge of the ice sheet, and they don't smear it in depth at all. And now, when you're going in depth in your original thing, when you had 40 layers, how deep did you put it?
I was put in at 1,000 meters. for
So
the
so
deep experiment.
uniformly mixed between 0 and 1,000, or just like
No, just
it
at
just goes
1,000
in
meters.
at
Yeah,
1,000 meters. So like
yeah,
the
it was kind of the
one
extreme
layer-
case.
Okay, okay. And then when you're doing your analytical, you're just putting it in the top layer versus the bottom layer.
Yeah, exactly.
Okay, okay.
Yeah.
Yeah. So I mean, so one of the things that is relatively easy to do in RGCM would be to change the depth over which this water is spread. You know, right now I think we spread it over 200 meters. And we could do some tests where you make that all in, you put it in you know, you put it in the first 5 meters, or you put it in at 1,000 meters. 1,000 seems pretty deep for the bulk of the water, though.
Yeah, I think 500 or 600.
Yeah, well, on average, obviously, it's not that, right? Because icebergs melt all over their column. They don't just melt at the bottom of their column. But I'm working, actually. We're working on a paper that's trying to be more data based on this. And so Twyla Moon and Dustin Carroll are working on trying to provide kind of more observationally based depth profiles of where iceberg melt comes in.
Yeah, that sounds really interesting.
Yeah, well, it's more complicated than one thinks, of course. Well, unless you've thought about it before, in which case you already understand how complicated it is. But yeah, I mean, with there are some things that we could do which would be interesting. Now, the problem with doing this in a coupled simulation, though, is that if you're going to change the input of the climatological fluxes, then you have to have like whole new PI controls, which take forever to run.
Right.
So, but then it's a little bit weird just to do it for the anomalous flux, but not do it for the climatological flux.
Right.
So I guess
Yeah.
I get that maybe that isn't so terrible. Maybe you could do it that way. There's this other model effort that's called the Sophia effort. Have you been paying attention to that?
No, I'm not familiar with that.
Okay, so that's Neil Swart. I'm sure somebody can send you a link to their paper. But the idea there is to do a whole bunch of Southern Ocean freshening experiments with CMIP class GCMs to see what it is you should be doing and how sensitive the models are. And it turned and I think the preliminary results are, you know, depending on what your background stratification is, you know, the same freshwater can have a very different impact. So perhaps in your sweep of parameter space there, you could have a look at what the effective stratification is for the different GM parameters, and then see whether there's any difference in what happens to your inputs as a function of that.
Yeah, that's a great point. Yeah, that's something that we've been looking at, trying to look at, like, basically these different responses can be explained by metrics like with buoyancy frequency and things like this. The answer is kind of, which is why I didn't show it, because it's not quite a super clear story, but I think that's definitely part of the story, or at least that's kind of my feeling from some initial looking at it. So yeah, that sounds really relevant. Thanks.
Okay, yeah, we'll be interested to see what you come up with there. That's yeah.
That's good.
Okay, thanks.
Awesome. Yeah, thanks for the questions and discussion.
Do you have any other questions?
I'm just going to put in the Sophia paper into the chat if somebody hasn't done that already.
I think
Damien beat you.
Damien beat me?
Mhm.
That Damien. Okay, there we go. Thanks, Damien. Yes.
Thanks.
But anyway, but there's an effort there that's kind of interesting. So you might want to start to plug into that.
Yeah, sounds great. Thanks.
Okay, I guess we can stop there. Any question? So yeah, thanks again, Aurora.